Hello, everyone. Welcome to this new talk on the second day for the JConf Peru 2020. We are here with Dennis, and he's gonna talk about a little bit about the best country for observing the Northern Lights. This is, will you tell us, Dennis, what this is all about? This is not that typical name for a conference.
Yeah, so first of all, I'd like to say thank you to people who stand behind the JConf Peru, people who committed themselves to make this event happening, especially like in this uncertain times. As you may notice, like lots of conferences being canceled with no online replacement, but still we're here at the JConf Peru, and not just to promote ourselves and things we would talk about, but to stand for the Java community globally. And I also welcome you to the day 2 of the JConf Peru. Um, let me before going into the talk, let me introduce myself. My name is Dennis Makogon. I'm a principal member of technical staff, a member of Java platform group who is responsible for Java development at Oracle. With some of you, we probably have met around the world when it was possible at the Devox, JFocus, or any other JCons or Java user groups in the US if you have been there anytime in 2019. Um, so, as many of you, I am a software engineer, meaning I write code for a living. But alongside with my work, on my spare time, I do the landscape photography as a hobby. But people on the internet call me some kind of like a pro landscape photographer. Well, maybe because my photos has won very prestige awards. And the latest one was the best drone photo of 2019. Like maybe this why. Like who knows? So what's this all about? What's this talk will be about? You're here to listen pretty interesting story of how my both skill sets of software development and the professional landscape photography aligned together, and how this type of a collision turned into a great story of the Northern Lights hunt. So this talk about the technology that I've chosen to develop a case study related to some kind of an awards, yearly awards that I've established in 2019 that I will talk a bit later. But it's all started with a very simple question from a friend of mine. Which country is the best to visit and witness the Northern Lights? I was kind of like uncertain to what to tell him. So I told him this: pick the one you like the most. Like go to Alaska, go to Svalbard, Iceland, Norway, Russia, Finland, Canada, Sweden, Greenland, north of Scotland, and the Faroe and Shetland Islands. If you haven't been like to any of those, just pick the one that will fit your budget. Uh, but to be very clear, from the point of view of physics, the fact of the Northern Lights' presence in the sky is a coincidence of multiple factors. So the Northern Lights phenomenon, those lovely dancing colors, color wave in the sky, is something that can be described and expressed as a set of measures, basically some kind of a numbers. So I ask myself, can I answer my friend's questions in a manner of a software engineer with a certain background in data analysis? So from that moment, the answer to the question which country to visit was nothing but a state of a system defined by a set of parameters and expectations that can be combined into some kind of like a mass equation. The result of solving of that is the exact answer where to go. So I decided to write a real theory that I haven't been doing this since university. So I really beg you for an excuse if it's not very accurate, but this is what I found. The form I wrote this, it was the most comfortable form. So as you can see, the whole case, the whole um, all this case study is kind of all about matching data and calculations and a bit of certain assumptions. So in order to make, sorry, but this is how the idea of the best, the Northern Lights Awards was born. This is like an overall attempt to give an answer to the most simple in the most simple enough form that can be consumed by non-technical people, because the whole theory of the Northern Lights requires a lot of knowledge about our sun, Earth, its magnetic fields, and a bit of electrophysics in general. So if you want to read the whole thing and take a look at the code and the results, I encourage you to go to the GitHub. You can scan the QR code or just take this URL, which basically the same as this QR code, and get to the case study itself. So I don't want to waste your time on how this works and what the algorithm is. You can, but I'd like to highlight some key aspects of it. Before we'll deep dive into technical details, I'd like to acknowledge two organizations. First is the Dark Sky API. If you haven't heard about that, it's probably one of the best weather forecast service that provides data, which does have a REST API, and using this service, you can pull the historical data for the weather forecast, for location, for the particular hour, and etc. And also, I'd like to acknowledge Helmholtz Center of Potsdam. This is a huge German university. Their work related to studying Earth and its magnetic fields and any influence that happened to our Earth from and the influence, the impact that comes from outer space. And let's start with a very simple key aspects. So the visibility of the Northern Lights is very dependent on when, basically the season matters. Where I would say far north, pretty close to the polar circle, or just go beyond that up to the North Pole. And what conditions should be there. So basically, in order to, if you ever was curious about the Northern Lights, you probably noticed that the sky should be very clear. The temperature should be low because you'll be around north. The visibility should be pretty straightforward, and as far as I can recall, the visibility should be like around 32 kilometers. This is like what human eye can, this is like the maximum distance of what on which the human eye can still recognize the objects, or at least see them. So these are like kind of three things that we are not in control of. But as an engineer, as engineers, we do make decisions of which technology to use to accomplish our tasks in the most comfortable way, in the most efficient way. But the term comfortable is kind of tricky here, as it actually declares a set of demands to the technology, and it has to comply like on 100%, rather than just go above some abstract desired threshold. So the technology should be very comfortable to work with anything I will be talk about later. And these requirements are, first of all, the technology must be comfortable enough to work with sequences. In the case study, each country is represented by a set of GPS locations, 9 or more. Each GPS location is described by 8 daily measures provided by Helmholtz Center. Each daily measure described by an hourly weather forecast measures during autumns, winters, and spring seasons. So it's like 226-ish days. So at the very minimum, for a single GPS locations, there would be like at least 3,000 measures. So, and depending on the number of the GPS location for the particular country, the amount of measures would go beyond 18,000 measures per year. So basically, we take all the necessary measures through the winter season and then just get basically summarize what we have there. What are those sequences? So it all starts with a sequence of a country-based GPS locations that those GPS locations are an entry point to the further sequence. The GPS location sequence expanded with the weather forecast bound to the particular date and the particular hour. The other thing that should be technology be comfortable to work with are pipelines. So ability to work with data, with ability to um, build a reusable data pipelines is a very critical feature, as the whole problem solving algorithm in my case study is a set of sequence perceptrons. So if you haven't been familiar with like machine learning, so the perceptron is the representation of human brain neurons, and this is how like in the computer science they are being represented. So the perceptron could be whatever you like. It could be any mathematical operation that takes some input and then provides you a result, or multiple inputs with a single result, and etc. So whatever it takes some input, does some operations on it, and then give you a result is a perceptron. So the whole algorithm is a set of sequence perceptrons that process multiple point connected data sets from the dark sky API and from Helmholtz center of Potsdam into like a compressed joint country-based statistics. So what does it mean? That for each country, we need to take every GPS locations for night hours only for the particular months or every month within the night season. We need to get weather forecasts, and then we need to filter them. We need to filter the data based on the threshold of the magnetic field disturbance. Basically, the magnetic field disturbance is something that this is like the very simple a measure that defines the visibility of the northern lights, and basically defines a physical belt that starts from the North Pole and expands towards south. Basically, each belt defines its own magnetic field disturbance value. And it means that in the particular belt, let's say like if Kp is 2, then the northern lights will be visible only far north. So let's say like Iceland and Svalbard. But if it will go like 2.5 or even 3, it will be around like Norway or even far to Sweden and Finland. So this is like the whole pipeline that I required to write, and I had to I demand from a technology that this pipeline should be reusable, and then all I need to do is just feed the data through this, and then get the statistics per month or get the final summary statistics by the year. The other thing is parallelism. Since the case study is some sort of a yearly challenge, the technology must be capable to run perceptrons in parallel. The good thing is that the data in my case study is quite efficiently splittable, because at most of the times the data points in the data set are not dependent between themselves, and they can be the perceptrons against those data points can be executed in parallel. So technically speaking, each country can have its own pipeline that must be capable to be paralleled to run the perceptrons for each GPS location, for each weather forecast, for night hours, to get the filtering, get the weather filtering, and etc. So comparing to just to the to the regular to the regular pipeline, all I need to do is to have a way to say to the technology, from this particular point, I'd like to have the whole data set processed in parallel in the most efficient way. The other part that I want to mention here is that both the Helmholtz Center and the Dark Sky, they provided their data through the API endpoints, the HTTP REST API in particular. So in the context of parallel pipelines, it's very important to reduce the time on the blocking HTTP calls, ideally with some kind of a non-blocking technique. And the last part, but not the least significant, is the type system. Um, so all I wanted to see is this to have from the technology is the same API to work with. So I don't really want to pull my hair out of my head just because something is not supported or require me to write a ton of the code to get a simple value that I can work with. And in particular, I'm talking about just one example from out of many is the time format, which is RFC 339, which might not be supported in various technologies, like programming languages in particular. So I need to get a bunch of dependencies in order to get like a data type to work with, like the native data type. And the winner technology here, probably it's too obvious, I guess. Yes, it's Java. Java for data science, data analysis. So don't you say you're not surprised, like, aren't you? These are like there are like multiple reasons why. And I'm gonna list out some of them that I found critical for such tasks and case studies like mine, where you have lots of data that needs to be processed in a manner of parallel pipelines. Streams API. You probably all of you you're familiar with that. One of the greatest things that actually happened to Java Collections framework was an introduction of Streams API. A stream doesn't store the collection, but it just represents a pipeline that I was requiring of the perceptrons applied to each item from the collection. So all I had to do is to define a set of perceptrons and then a final collector, which will basically provide me a result of the whole case study for the particular country and a year. So the best thing that streams are really cool. So just there's nothing to say about that, but it's not all. The Streams API utilizes common fork join pool by default to run processing units against a number of threads in a form of pool. So no matter what you do, as long as the data of your data set can be effectively distributed with a parallel stream, the workload could be divided within a configurable amount of threads in a fork join pool. This kind of a technique potentially can give you a boost in the performance in the time as well. However, it might not be always like that. We all know that the runtime is fast. The only slow thing is like your code. So the effectiveness of the parallel executions can be expressed in a pretty simple way. As long as the computational cost of a single item processing through the whole data set is higher than the overall infrastructure provisioning overhead, and the data set is effectively splittable, then the data set processing should be considered as to be executed in parallel. I know it sounds a bit like very like a thing you ever heard in university, but let me explain this. If an operation is very simple and the execution cost is lower than the overhead of a thread provisioning in a fork join pool, then the data set must be very big to make the parallel processing worthless. It also works in the other way. If a computational cost of a single item processing is high and the data set is effectively splittable, then the size of the data set might not matter in order to make the parallel execution worthless. And just let me just give you an example. So imagine that you have a data set of integers, and all you have to do is to increment each of them. So the incremental operation is pretty simple and it's cheap comparing to the amount of memory and the time required to provision and the whole infrastructure for the parallel stream. Uh, in this case, the data set of your integers must be like very big in order to make the whole processing in parallel worthless. And it also might happen that the whole stream processing in a sequential way can be more effective than running the parallel one. So you're probably asking yourself like what I mean when I'm saying like effectively splittable data, effectively the distributed data. So let me explain this. As we all know, the most efficient and splittable collections include array lists and hash maps. So the data structure tend to be efficiently like splittable if they internally support random access and the efficient search, like or ideally both. So on the other side, if it takes longer to partition your data than then process it, then the effort is wasted, and it means that it's better to run the stream processing of your data set in a sequential way rather than in parallel one. And I also want to mention that there is a very good thing that will happen to JDK and threading framework later is the project Loom, which is with the alpha build, the pre-builds of this project is already available at openjdk.java.net. So if you haven't heard about the project Loom, the main goal of that is to re-implement the whole threading in Java, but not to change the APIs to make the transition to technology very smooth. But the internal tool implementation of a thread already has changed. So before Loom, all we have here, we have an operation system thread and a JVM thread. So basically, they are equal. But with Project Loom, the JVM will provision some kind of what do you call the carrier threads, and whatever threads you will create in your application, those threads will be a virtual threads. So if you have lots of operation, the IO operation that happening in threads, the carrier threads will switch the context of execution between threads whenever the blocking IO operation will happen in a thread, to give a time to another thread to continue its execution if there are such threads. If not, it will await for the response from the other side of an IO pipe, or whatever that be, a file, socket, or just call it whatever that is. So in my particular case study, since I use the Dark Sky API service and Helmholtz center the magnetic field disturbance data, it actually gives me a pretty good improvement in terms of the IO operation, because I have lots of HTTP workflows internally to get the weather forecast, get the magnetic field disturbance, and etc. So if you haven't checked that project, I really encourage you to go that and then just read about that, or go to YouTube and then just Google Ron Presslers, who is the lead of this project. He's any of his presentations, they are great, and they explain you what the project Loom is and how it will work with threads, and how other applications will work with re-implemented threads, and etc. So let's go back to streams. The other part of streams and the pipelines is that they are memory efficient, because a stream just stores its own metadata and doesn't store the collection or data set. The only moment when your application starts gaining in memory is when you turn your stream into a persisted type. So basically, to be very specific, when you call a collect method on a stream, um, so yeah, there are like their streams as the pipelines are very memory efficient. The other part is comfortable API interface. Depending on the task that you have, a stream declaration could potentially have multiple forms. Just recall for each method, the recall map signature and the collect. So for each, it wouldn't produce you anything. It just returns void, void type, and uh, all you have to do is to process your uh, items from your data set and just do with them later you want to, but you have to store them or just do any operations that will start any other workflow later. um, when you call a map or flat or filter, the output is another stream. So basically, using this type of method, you can declare a pretty good and pretty uh, uh, complex stream that will be easily debuggable, and you can actually do this with the JetBrains IntelliJ already in a visual form, but not just with your debugger. So streams have a very clear API that you can use to build the pipelines for your data processing, and they are very verbose because yeah, it's Java. It's very verbose all the time. Um, and streams are reusable, but by design, streams were developed in a way that they are not reusable. So if you would try to rerun a particular pipeline again, an exception will be thrown saying that the stream is closed. However, there are some kind of a tricks that can help you to write a reusable streams. You have only like two different ways. You can reuse a function interface that basically will give you an ability to create a parameterized function that you can feed the particular the particular collection, and then it will run the stream. It will run the pipeline against that collection. And there is another supplier interface, but I don't really like that way. But because you have to hard code the collection itself into the supplier, but you can rerun with the supplier. You can rerun the the whole collection against the same data set as many times as you like. So I want to outline that the Java is awesome. So yeah, we all know that it sounds very, I'll say it sounds pretty obvious. Just imagine that you have so many data points and that require to be processed, mapped, filtered, and collected at once. And things are getting even better, taking into account that in my particular case study, the data points are not dependent, meaning that I can make the whole execution go in parallel without any problem. Oh, and the ability to run asynchronous HTTP calls, HTTP requests, starting with a built-in HTTP client into JDK11 is amazing. Even without Project Loom right now, it's already give you all necessary API methods and all capabilities to improve your IO operations, the HTTP routing in particular within parallel pipelines streams. And going back to the very beginning of this talk, uh, it's all started like with a very simple question. Which country is the best to visit and witness the Northern Lights? So after a month, I gave my friends an answer. So far, Finland is the best country to visit by just number of days, with the suitable weather and corresponding magnetic field disturbance that give you a pretty clear visibility of the Northern Lights. But a few years ago, Iceland was like the number one here. because but the weather has changed dramatically through the year. But now like it sits on the second place, and Norway is now on the third place. Although I'm in love with the Northern Norway, the Tromsø, Senja, and Lofoten Islands, which are known as the best and the most beautiful islands in the world. Sweden like is on the last one. Too few places to go, too few days with suitable weather conditions, and etc. So that's pretty much it. So I encourage you as a developer and the people and the person who has a hobby to do the next thing. Try to apply your development skills like as I did. I took the Java and the very um, widely spread assumption that the Java is not suitable for any data science or data analysis. And they basically proved to those people who say that with the appropriate amount of time and the particular techniques, there are so many ways to make the data processing way more efficient. And basically, I tried to demystify the whole myth about that the Java is not suitable for this type of operations because, like, if you ask any data scientist or data analysis, he would say like Java is not suitable. But I would say that that person haven't tried to do something that he got used to do in his regular his regular tasks. So yeah, that's it. And probably like I guess we're done here. Hope you find this talk kind of interesting, even though it wasn't very packed with so many technical stuff. But I tried to highlight some cool stuff about streams, about the parallel stuff, and etc. So if you want to learn a bit more about the parallel streams and the theory of the efficient parallel streams, I encourage you to Google a Doug Lee paper about the parallel collection. It's very useful, especially if you do concurrent operations with Java and streams are a part of your applications. I encourage you to visit probably one of the best Java blogs on the internet right now. It's called Inside Java. Subscribe on my Twitter, on the Java Twitter. And if you enjoy my work as a landscape photographer, probably just go ahead and check my Instagram. And probably that's it. This is like the end of my talk. I really hope you enjoy that, honestly. So if you have any questions, just shoot me with them. And that's it. Thank you.
Hey, Dennis. Yeah, thank you very much to you too for this awesome talk. It's actually something not that we don't do that often, just to try to mix whatever hobbies we have with the development work. This is something we keep separated maybe because we think work is something different from our real life. So it's really awesome to see someone that is actually combining the two things and making the best of it. So thank you very much for that.
Thank you
Um,
for giving me opportunity to speak here. I really hope you people who attend this conference will enjoy this online or later as a recorded version.
Yeah, totally. Of we don't have any questions right now, but I do have one. So I see that you were doing a lot of I mean, you were trying to answer questions by doing actually scientific and engineering with the Java and all that. So you were talking about you ended up saying that Finland was the best country to see the Northern Lights. And I was wondering, you said that it was because of a time frame of a place, and what were the? I mean, did you create a model? How did that work? Yeah,
So can you repeat the last part of the question? Like, um, I
I know you
yeah.
use. Okay, yeah, you explained it, all the calculation and all the work
Mhm.
you did with Java. But was that how did you? I mean, what was the starting part of it? How do you came to say, okay, I'm gonna start calculating this, and I'm gonna take account of
Okay.
uh, I don't know
Mhm.
the how
I,
it had the lights and all that. I don't know.
okay. So how did I start it? So probably the simplest answer would be as a landscape photography, I was very curious about the northern lights because it's one of the greatest night shows that happening on Earth on the on the North Pole and a few areas around that, and on the South Pole as well, which called well, I don't recall what the exact name for the. It's not like it's like Southern Lights. I don't recall that actually. Um, so when you want to hunt the northern lights, you have an application on your phone that basically gives you an online data showing that how the aurora basically walks through the earth, and basically you see the belts of you see the areas that are impacted at most. So in a very simple day the belt would be just green, but if the sun activity was very intensive, the aurora would start glowing with some pink or red colors. So I decided just to find a scientific way to define uh, how to find how to find a place which is the best to witness. So as far as I can, so at that moment, I already know that the Northern Lights is defined by the location, by the weather, and the sun's activity. So basically, these are three measures. Since all of these three measures can be expressed in basically in the numbers, so they can be combined into into math equation to basically give you some kind of a probability of the that you can witness the northern lights. So, and since you actually cannot predict the upcoming aurora visibility because the weather can change dramatically, the wind can change in an hour, in a matter of hours, and the weather can change, and you basically can see nothing. But using the historical data that has been provided by Helmholtz Center and the Dark Sky API service, the weather service, you can basically make yearly statistics to see which month was the best one, which country was the best one, and for how long you need to go to a particular country to see the northern lights. So in the case study they've published on the GitHub, it basically says that in order to see the northern lights in Norway, you just need to spend like 4 days in let me just recall, the February was the best month for Finland. So you need to only stay like 4 days up north in Finland to see the northern lights. In the meantime, in order to see the aurora at least once, you need to go to Iceland for 10 days, and for like 7 days to Norway, and once again in a particular month. And those locations that I've collected, those are locations that people reported that in those locations they have seen the aurora. So all I have to do is basically combine, let's say, like 4 different measures and and the particular weather conditions. So basically, I need to identify what is the cloud coverage is. So like say if the cloud coverage is more than like 20%, the chance of the visibility of northern lights could be dramatically decreased because like if there is a wind, the cloud will start moving, and you need to basically identify what's the direction from where the northern lights coming, and etc. It's like so many different things. This is why it's called a hunting, because you basically go and hunt for those lights. And so the other part of my hobby as a landscape photographer, I get used to do a landscape workshops around the world, and in the wintertime in Europe, I've got used to take a few groups of people who wanted to see the aurora, and they basically take them to the particular location in a particular month, somewhere on the edge of the February and March, and within those months, we basically spend like a 2 weeks up north, and then hunting the aurora between the location that I've already collected. And I know that in particular month, for the last 10 years, the visibility of northern lights was very great. So I'm doing a very reckless assumption that having that knowledge of the previous aurora seasons, I would try to, and I'm basically making an assumption that I will see it again in the same locations in the same day. Once again, it's pretty reckless because I didn't have any idea of what the weather would be like. No, there is like no service, the weather forecast service can give you the exact data in a real time, because they all do a mathematical assumption on the weather models they have built for the particular region, and etc. So um, it does sound like it's kind of complex, but when you nail down to every bit of the data you need to collect and how to join this data, you will see that it actually it's pretty simple as long as you understand what you're trying to get out of it. So that's why I tried to write a theory for people from people who've been familiar with tech, and I established the Northern Lights Awards, yearly awards for people who's not from tech but they wanted to go to the north and see the Northern Lights. So yeah, that's probably how it started, and this is how it ended in a form of a talk and the small theory that I've declared.
Indeed, very interesting, honestly. We have another question here from
Sure.
Omar Bertrand Silva, and he's asking if you're planning to make this technology available for other people, for like, for example, observatories, and if this is the code is published, is available for everyone, like in GitHub or something like that.
Yeah, this is like an open source technology, so you can basically take that and use that. Although the on the GitHub, the very important thing is the paper itself. But if you want to reuse this data, there's supposed to be some additional work applied, because I made this data for myself, and the paper is something that will be available, that considered to be available for any other people. But I would say there has to be a very clear understanding whether this technology is required for the observatories, because as you notice, I've been talking about the data that the data from Helmholtz Center is the historical data. They basically publish it by the end of the year, um, and the weather forecast that I've used from Dark Sky, they also this is like historical data. So all I get is a historical statistics model of the northern lights in the past, because uh, I would say, I will be honest with you, there is no way to make a prediction model that you can reuse to find out whether you can see the northern lights in a particular day in a particular location, because there is so many things that may impact the visibility that you cannot predict. And it's kind of tricky thing, but this is something all photographers or all scientists have to live with. There's still no way to make this possible, and there is no work like papers or scientific papers like the real one from scientists, because I'm not really a scientist. I'm just curious developer and a photographer, as like a hobbyist photographer. So this is what I try to do, and I really hope, and I'm really glad that you find this interesting. And so if you want to expand this discussion in offline, I'm really glad to do this. Just find me on. You can write me on Twitter. Or you can take email from the GitHub and just reach me out. I'll be glad to do any conversations. Thank you.
Yeah, for the people who's listening now, I'll say, I mean, so if we are going to go hunting the Northern Lights, we have to know that there is some level of uncertainty. So we may or we may not, depending on the weather and all those conditions. Do you have the Git repo in one of your key presentations so we can share it to the public?
I will. I can put that on a speaker deck and then send a link in a Slack if you like.
Sure.
Okay.
Thank you.
Yeah.
So yeah. Well, that was pretty much all the questions that we have. Uh,
Okay.
I just gotta say thank you very much again for having, for spending this time with us and sharing all the knowledge and all the information that you collected all over this time and where you were doing this. And you're still working on that? I
So
mean,
basically,
improvements and all that?
so I'm waiting for the December. This is like would be the day when the Home Health Center will publish a new data, and then I will do another one yearly.
That's great. So
Yeah.
looking forward to see that. And again, thank you very much. It
Yeah,
was a
thank you
pleasure to
for
be here.
giving me a chance to speak here. I really hope you find this talk interesting. I know it's not something that you got used to because like at every conference, the things are packed with lots of technical details, and the output of it could be very challenging. You need to rewatch that. But this, I tried to make some kind of like keynote that you will find interesting because it basically combines your professional skills and your hobby, because like every person on earth should have hobby. I know, I do understand that we are living in various at certain times. The traveling is not something very possible right now, but when the whole thing will get back to normal or in a new form of what that would that be later, just take your time, travel to Antarctica because probably from Peru it's closer than the Northern Pole, because you also can see the Northern Lights from there as well. But probably you might even see the Northern Lights from Ushuaia, which is like the closest the end of the continent. But I'm not certain about that. I need to basically look at that with the locations and the South Pole belts, compare them to the North Pole. But yeah, just if you have time, travel to Europe, travel to Iceland is like the great country, especially in winter. And it's great for the Northern Lights because it actually was known as the best country for the Northern Lights, but the weather has changed for the last like 5 years, I guess. Lots of snowstorms and etc. It was very good for observing Northern Lights.
Yeah, I definitely am gonna put that on my to-do list. So, yeah, well, uh,
Yeah,
thank you and
thanks. Have a good day, folks.
good day to you too.